several small forces everywhere when you do the section. So it could be like F1, F2, F3, F4. It's actually everywhere on the surface, depending on whatever direction it is. And it can be, what we can do is we can try to find equivalent system from what you learn in your static class. And that equivalent system itself, you will have your FR, you will have your MR, and then the FR itself, we're going to say that, hey, let's cancel that. And that FR can be split into two different components, and we get rid of this FR. Now the FR that is perpendicular to the surface, we actually have the term N, that is a normal force. And the FR itself, that is perpendicular to the surface, we actually call it a V, or the shear force. And then of course we can get rid of this M. And the M itself can be split into two different components. MR, that is perpendicular to the surface. We also could have this MR that is perpendicular to the surface. The one perpendicular to the surface, we have a letter T, or that is a torque, but it's a moment perpendicular to the cross-sectional surface. And MR itself, that is parallel to the surface, we call it MB, or the bending moment. So what happened here is this is going to be chapter 4 in your textbooks. This would be chapter 5 in your textbooks. And this together would be chapter 6, 7, 8, 11, I think. There would be like 4 different chapters for the shear force and the bending moment. But before we get to that, we're going to try to understand the concept first, the concept of having a cross section. So let's say that in this special case, we're going to look back and say that, hey, if you pick up any small element at all on the surface, any small element would exhibit different forces on the surface. We call it finite element. That means it's very small, very tiny. And on that surface, the force itself can be split into 3 different components. We can say that, if you have an axis, let's say that this is X, Y, and Z. You have the force in the Z, you have the force in the Y, you have force in the X on that top surface that you saw. Now, the thing is, on just that surface, the area here, area is a vector. By the way, if you, I don't know if you learned that in your calculus class or not, but let's say if you have vector RA and then vector RB. The two products RA cross RB will get the area, and that area is this is going to be the area, and the direction of that area is actually perpendicular to both RA and RB. This is a cross product. So A itself is a vector quantity. So since area is a vector, we call that this is going to be area in the Z on the top surface. This is going to be area in the Y. This is going to be area in the X. The direction of the area is perpendicular to the surface, coming out of the surface itself. Now, we do want to study those. Again, the four different components that we have: normal force, shear force, bending moment, and everything in the future is just to find those finite in tiny element. The purpose of doing that is that the whole process will go to that tiny element. At that tiny element itself, we come up with another quantity. Let me have this right here. Going back into two-dimensional, if you have the surface, let's say for example, right here, the axis X and Y. On this X, right here, this is area X. If you have the force coming out, Fx, you will also have Fy. Again, Fx itself, eventually you're going to be calling that a normal force. Eventually you will be calling this a shear force. But all in all, what happened here is that we're going to be coming up with properties. A property is the intensity or the force per unit area. So this would be the stress in the IJ. And that's going to be the force in the J over the area in the I. So it means that you will have stress X, so it means the force in the X, area in the X. You will have stress XY, F in the Y, area in the X. And when we have that, the way you do the write-up is going to be a little bit different. We're going to have this called stress XX. And rather than having the arrow like that, we're going to be calling this stress XY. This is going to be a different way of drawing the arrow. So the first indices will be the area. Second indices will be the force. Now, usually, if you understand the concept, the force has to be in balance. It means that if you have N on the right-hand side, your N has to be on this as well. If you have B going up on the right, to have it balanced, you should have the shear force going down as well. So just from here, I will be able to say that, hey, on the left, I should have stress as X as well. I should have the stress, this is going to be YX as well. And we will find out that the stress XY must be equal to the stress yx. Actually, I didn't do it right. Sorry about that. Let me do it differently. Because I kind of jumped ahead. So this is the stress, area is minus x, direction is minus x. So it means that minus x must be equal to the x itself. So a lot of time, rather than doing it this way, we would be writing it as stress xx. And to make this right, this right here, I'm going to put it in different color. So this is going to be stress minus x minus y. And then as it turned out, minus x minus y must be equal to xy as well. So you see that in terms of the balance of the force, it will transfer to the balance of the stress as well. And from here, the two right there, I'll put it in maybe green color, will create the rotation on the element like this. Those two. The object itself is in equilibrium, which means you have to have something to counterbalance that. And that something must be, going a different way. So what's best? What happened here is that I'm going to have this shear force over here as well. Shear force over here as well to make it balanced. So it means that from that shear force, I will have this stress yx as well. And over here, this is going to be stress minus y minus x, which is stress yx. And then since we know that the two has to be equal, so stress yx must be equal to stress xy. So of all of this, even though we have 4 different surfaces, when you start doing all of this, you will end up having stress xx, stress xy, and stress yy. Those are the 3 that will be independent. The rest will be dependent. Okay? The rest will be dependent. It means that right away you would be able to transfer whatever complicated drawing or complex drawing of the stress element into just stress xx. Stress xx, this is stress. Let me do a better drawing of the sigma. This is stress yy. Stress yy. And over here, in terms of the shear, they will all be the same. So rather than writing all of them. So in order to make sure that you understand all of these are the same, I'm going to highlight this in pink color, that they have the same value. The pink color just demonstrates that all of this would be the same. Stress xy. Now, stress xx, stress yy, stress zz, if the index is the same, we call it sigma x, sigma y, and sigma z to make it shorter. Those are normal stress. That means the force will be perpendicular to the area. And we will have stress xy, stress xz, stress yz. To make things easier for us, we're just going to be converting that to tau. By the way, this is sigma, and this is tau. So we'll be calling it tau xy, tau xz, tau yz. Those are shear stress. This is in 2 dimensions. In 3 dimensions, it will have a total of 9 surfaces. Well, is it 9? No. 9 values, I would say, not 9 surfaces. I will have this 1, 2, 3 surface, 4, 5, 6. The total of 6 different surfaces in 3Ds. By the way, this is x, this is y. And if we continue with the same protocol, x, y, and z, you will have sigma x, sigma y, sigma z as a normal stress in 3Ds. So it means that we have sigma x, sigma y, sigma z. I'll put it this way. And I will have, this is going to be, on the surface that we see, this is going to be tau, rather than calling it sigma, tau xy. On the top will be the same tau xy. So again, this will be tau xy. And again, tau yx and tau xy will be the same. So rather than having that there, I will put this in like a little gray color, because it's the same. And on this surface, I will be able to draw this, and this is tau xz. Again, tau xz will be coming here, so this is tau xz. And we will have tau zx, which is the same as tau xz when they balance each other. And the last one would be this. This is tau yz on the top. So this is going to be tau yz. And tau zy would be the same as tau yz. This in 3Ds we call it general state of stress. Right. This is general state of stress. And there are 6 independent variables. 2Ds would be 3 different, well, 3 independent variables. 3Ds, 6. But the total that we're missing would be in those gray color, or I'll highlight them as black. These are dependent. So state of stress would be those. Now, in all the chapter, the whole purpose of studying this, whole semester is that each chapter that we go through, we will try to find how the N transfer to the stress. How to be going into the stress, how the bending moment going into the stress, how's the torque going into the stress. So the stress calculation for each chapter would have their own formula, their own techniques, and from having those own techniques, in the end, you will be able to get this stress element. So this, again, we call this stress element. So we talk about the stress element first. Later on, once you start doing different chapter, you will get to do the sections, you will get to do the, well, let me show you the flow. The flow of each chapter is this. You will have equilibrium. And with that, you will get the normal force, the shear force, the torque, or the bending moment. And from there, you will get stress profiles. And from there, you will get the stress element. So right now, we're talking about the element first, which is those elements right here. And once we get a hang of the stress element, we will go into each chapter and we will work forward. So any question about the terminology so far? If you don't have any question about terminologies, let's do a quick test to see if you understand what's going on. So right here, if I have a tiny element, I have this as my x value, this as my y value. Again, my axis can be different. And I have 20 MPa over here. And I have 10 MPa, and I have this is as 30 MPa. My question, quite straightforward, is for you to complete this stress element. This is an incomplete element. I want you to list out what is the stress x, stress in the y, tau xy. And I want you to complete the element based on the information that I gave you. So this is a start. I'll use a different thickness just to show you. Just to show you the answer. But when you actually do the drawing, you don't have to do different thickness. Okay? So at this point, you have, we can keep looking at this. You have 10 coming up from the bottom. So on the top, this would have to be 10 MPa going down. So from that, it means that the positive x area, you have 10 going into the surface, so sigma x would be negative 10. That's going to be the first thing you have to acknowledge. Second one, you have 20 MPa to balance the one that we have from the right. So So it means that right here, you will get a positive 20 MPa for the sigma y. So 30 MPa going down on the right. This one will have to be going up. It causes the rotation clockwise, so you have to have a balance to go counterclockwise. The shear stress would be head to head, tail to tail, always. So it means that right here, this is also 30 MPa. And you have positive x. If you look at the top, this is positive x. And then it goes to positive y. So tau xy itself is actually positive 30 MPa. Does this make sense? One more. Let's try this. I'll say that this is y and this is z. I'll start with MPa over here. I'll have 10 MPa. I'll have 15 MPa. So this is sample 1. This is sample number 2. The two are totally independent. So complete the stress element. Complete the stress element and list out what values we have in the stress element. This is something, if you understand, you understand. So right away, this will be sigma y equal to minus 30 MPa, 10 MPa, and you have sigma z equal to minus 10 MPa as well. And this is going to be tau by z, and that's minus 15 MPa. Because positive y is going to negative z. So right here, it's going to be the rest that you have to complete. You have to be able to, go forwards and come back, or go backwards, do the reverse techniques. So if it gives you, for example, sigma x, sigma y, tau xy equal to minus 10 MPa equal to 20 MPa equal to 40 minus 40 MPa. Right now, your job is to complete the stress element. is x, y. Exercise number 3. Again, things is quite straightforward. This is 10 MPa. This is 10 MPa. This is sigma x. 20 MPa. 20 coming down. Minus 40, that means positive x, negative y. So this thing has to point down. So this is 40 MPa. And the rest quite straightforward. You just complete the values. Anyone find this confusing? Let me know. Yes. What's your question? How do I know the direction is going down? Okay. This one, positive x. This one, negative y. So positive x, negative y, positive and negative, that's a negative. If it's a negative and negative, that is a positive. It's just like that. This is a negative. Positive, positive, that's positive. You can also imagine it this way. So let's say that we have this one, negative x, and right here, that is positive x. So that means this is a negative 10 MPa. Because, this is the area. This is the direction of the force. It's true on any surface. So once you get a hang of this, you should be having no trouble at all for the part that we get to the stress element for the rest of the semester. Okay, let's try example number 4. We're going to have stress x, stress y, stress z, 20 MPa, minus 10 MPa, minus 15 MPa. And I'm going to have tau xy minus 5 MPa, tau yz equal to 40 MPa. And that's it. So if I have this, you need to draw the three-dimensional element, and you need to be able to complete those arrows along with the number of the stress. So let's say we have x, y, and z. Try this. Again, two-dimensional, three-dimensional, same concepts. If you understood the concept of the stress, how we put the positive and negative in 2D, you should be able to do the same for the 3D as well. So try that. start with something easier. So in 3D, it's different than the 2D in a way that you only draw the stress on the surface that you see. You don't like draw it on the other side. So for example, if it's a 2D, you probably have to do this 20 MPa. You probably have to do the 20 MPa over here as well. But you don't really need that. So this one is okay not to show them because it's on the hidden surface. You don't need to show the hidden surface. So in a way, if you want, you can say that this is actually 20 MPa that you don't see. I don't ask you to write, but I'm just showing you that it's there. You just don't draw that. So again, this would be 10 MPa on the hidden surface. This would be 10 MPa as well. And this is like the hidden surface. And the reason why we don't draw on the hidden surface because it's going to get too cluttered. So right now I'm not going to draw this anymore. Let me just get this out. It's going to get too cluttered. Okay, so we have 20 minus 10 and minus 15. So it means that this would be 15 MPa going in. X, Y minus 5, so it means that this is going to be 5 MPa, and that means this would be another complementing. This is 5 MPa. Y, Z would be 40, so that means Y and Z would be 40 MPa, and that means this is going to be 40 MPa going up. Usually, when we have a shear, a single arrow is okay, but double arrow is okay as well. I mean, when I say double arrow, I mean the arrow with 2 heads or the arrow with just 1 head. Both of those are okay for the shear. Now the problem that we normally run into right now is that sometimes we do the analysis and we say, this is my X, Y, and Z, according to the picture. But then suddenly when you start working in different kind of machines, X, Y, and Z start rotating because your reference would be like your object, the car might be here, or your machine robot's arm might be like that. But then when you start moving, the arms, the X, Y, and Z axis start rotating. So that's going to be a problem with the analysis, especially when we do solid mechanics. So what happened here is that, let's say you do the analysis and we do a virtual section. For example, the virtual section is over here, is followed by regular X and Y. But then suddenly the machine fall apart, they broke down, they have fracture, and that fracture itself, sometimes they do it at the ankle. So sometimes we have that angle where fracture occur. So when that happens, it means that our best analysis is to create another axis called this is X primes and Y prime axis, and we have to again redo the normal force the shear force, and the moment on that new surface. And once you do all of that, you will be able to get the stress element on that new surface. But the thing is, this is going to be too difficult. That means each time you do the analysis, you have to do a virtual cut again and again. So rather than doing that virtual cuts, we're going to be looking at this small element. That small element would be the stress element that we start with. And that small element, I will put different color in here. And that element would be like this one, in light blue. So if we can analyze the square, we can analyze the rectangle. We can analyze the triangle within the square. So in this case, what happened here is that we're going to, do like a little zoom in, and rather than doing the new virtual cut on the whole surface, we're going to be doing the virtual cut on just that stress element, and it turned into something like this. And that virtual cut itself will be this triangle, the one that I have mentioned to you that I will do it in blue. That triangle will be just this cut. Now, in terms of this triangle, the concept is quite straightforward. If you have the area over here as delta A, trigonometry say that the area over here would be delta A sine theta. The area over here would be the delta A cosine theta. So the area is going to be in the ratio of the right triangle that we created in the first place. Don't worry about the mathematics. I want you to understand the concepts. So again, we start with the square and we cut the circle, we cut the triangle from the square. And once we cut that, originally, if we have this stress, the stress over here is still going to be on this side. So how do we do this quickly? Let me just draw this right here. On the left side, you're still going to have the stress in the x. On the y side, you still have the stress in the y. But the area over here would be the delta A sine theta. This is the theta. You're still going to have the tau xy. You're still going to have the tau xy. But the area over here would be the delta A cosine theta. Now on that surface, what we say is we think it has to have a normal stress, and we call that sigma x prime. This is x prime axis. This is original x axis. The rotation over here would be the delta as well. And we would have on this surface tau x prime y prime. And the area over here is just the delta A. Again, the sigma x prime, tau x prime, y primes, those are the stresses. Those are what we call the stresses on elevated in that point, but we do a different cut, and we call that the stress that we transform. So the fact is, we know the terminologies, we want to know what those are. The question is what those are. And it's quite a simple mathematics. I'm just going to show you very briefly. So again, I'm not doing this myself. What we do is we take a summation of the force. So the force itself will be, again, sigma x primes times the delta A. So again, this is the force along the x primes from here. And this is going to be the force along the y prime. So on that surface, you would have the force. So this one and this one. Actually, not that one, but which one is it? And this one. Then we try to find where that is. Y prime, tau x prime y primes times delta A. It's in there. Now, what happened here is that what we try to do is we're using this triangle, and from that triangle itself, we do the summation of the force equal to 0. You can do the mapping and everything, and this equation is right. And after you finish the derivation process, you will get the very critical formula that we use, would be those two formulas. And this is the formula for, again, this is sigma x prime, this is tau x prime y primes, and I only ask you to, well, not really memorizing it, but to know how to use it, okay? You don't have to derive this, just trust me that this derivation process is the correct one. You can, if you feel like you want to have fun, do the derivation yourself, that's fine. But know that we're only going to be using the formulation in the red color to do this. So, knowing that we're going to use the red color formula, we're going to show you this, okay? I'm going to say that, hey, if this is the stress element that we started with, let's say that we have 30 MPa coming in. We have another 30 going up. And we have this one being 40 MPa. This is X, this is Y. My question is, I'm blowing this up quite a lot. My question is, if this is elevated angle, 20 degrees, what is sigma x prime? What is tau x prime y prime? And then of course this is still your 30 MPa. This is still going to be your 40. And this is your 30 MPa. So my question is quite straightforward. X primes, tau x prime y primes equal to 1. Just in case you didn't get the formula, I'll copy it over to this page. Again, I'm too lazy to write it, to write this every time as well, so let me drop this So this is the formula that we use. You're going to be given the formula, by the way. You should not be happy about that. Because many people thought that they have the formula, and in the exam they just copy the formula on the formula page, write it in the answer sheets without filling in anything. They got nothing. They got 0 because they don't know how to use the formula. So again, formula is given to facilitate you, but doesn't mean that you should not know how to use them. So first thing first, your sigma x is negative 30 MPa, sigma y is positive 30 MPa, tau xy is positive 40 MPa. Those are things that you should be able to make the listing first. So once you make the list, the rest is quite straightforward. Sigma x primes would be minus 30 plus 30 over 2. I will put MPa all the way to the end so that I don't have to put like MPa every time. But you just have to make sure that you're consistent with the units. So again, this is minus 30, and then this is over 2. Cosine of this becomes 40, and plus tau xy, this is 40, sine of 40 degrees. This is in MPa. Now only then you can do this substitution. So first term would be 0. And then the second term would be minus 30 times cosine of 40 degrees plus 40 sine of 40 degrees. This would be 2.73 MPa. Quite straightforward, simple substitution process. Tau x prime y primes, again here we have minus, this is minus 30, another minus 30 over 2. I have to put the MPa at the end. So this is going to be 40 cosine of 40 degrees, MPa at the end. So again, what do we have here? So 30 sine of 40 plus 40 cosine of 40. So this is 49.9 MPa. Tau x prime y prime. Simple substitution. And you just put those values in there. 2.73 MPa. And this is going to be 49.9. Quite straightforward, right? I want to get to the point where we talk about maximum stress, so we will finish the maximum stress and then we'll take a break. So look at this formula right here. Let me copy this over. The formula that we have in here is actually what we call a parametric equation. Terminology is called that if you look at the sigma x primes, so for example, this is sigma x primes, this is theta, you're going to start having the values that going into a curve like this. Usually, sinusoidal, I forgot how to spell it. So similar to the sine and the cosine curve. So it's going to be fluctuating up and down. And for the tau xy, tau x prime y primes, it's also going to be fluctuation. But the value of the mean of the tau x prime y prime will be around 0. But then the means of the of the sigma x primes will be sigma average. We will get to that. The fact is, with the two equations that behave this way, I'll show you the plot later on. The way that the two equations behave this way, it means that you can find the maximum and you can find the minimum. Right? The same, you can find the maximum, you can find the minimum. Sigma x primes max, we actually call it sigma 1. It's actually what we call principal stress. Sigma x prime minimum, we call it sigma 2. And again, this is sigma 1 and sigma 2 we will call principal stress. It's just a maximum or the minimum. Tau x prime y primes max, we're just going to say that this is going to be in plane max maximum shear stress. That's going to be what we care about. Tau x prime y prime minimum, we don't really have a word for it, but sometimes we just call it just in plane minimum stress. Now, in order to find those mathematically, we just say that this is a functional form. It's a function of the data. So in order to find the maximum, you just have to take the derivative by data itself, set it equal to 0, and then you will get min or max depending on the result of your differentiation. Quite the same, tau x prime y primes is also a function of the data. If you take the derivative of tau x prime y prime by data, set it equal to 0, you can find max and min as well. That's the concept. So with that concept, we're going to take this rate function, the rate functional forms that we have here, and we will take the derivative of it and say that this is the del of sigma x prime by del data. The first term will be 0. The second term will be sigma x minus sigma y. Cosines, you get minus sine of the 2 data times 2. plus this tau xy would be cosine of the 2 theta times 2. Now this must be equal to 0 to secure the values. This is the dot value. So all of this, it means that if you have sine, we cancel the 2. Okay? If we have sine of the 2 theta over cosine of the 2 theta, that would be the tangent of the 2 theta itself. That would be equal to tau xy over sigma x minus sigma y over 2. So this is going to be the relationships that give you the maximum value of the sigma x prime. So it means that this one, I can kind of draw the triangle for this, and if we say that this is 2 theta, tangent would be tau xy. This would be sigma x minus sigma y over 2. We're going to be calling this r. The r itself would be the square root of sigma x minus sigma y over 2 squared plus tau x y squared. The 2 theta itself would be the 2 theta that will give you principal stress. So a lot of time we would call it 2 theta p. So we would be calling this 2 theta p. Which means that if you want to know 2 theta p, it would have to be arc tangent of tau xy over sigma x minus sigma y over 2. And this would be the angle that give either max or min. So what happened here is that you use this 2 theta p, or you're using this triangle to go back to the substitution of this. So again, sigma max or min should be having this substitution, sigma x minus sigma y over 2, and cosine of the 2 theta is going to be sigma x sigma y over 2 over dr, right? Cosine. And then you have a plus tau xy, and then sine would be tau xy over r. So max min would be, I would call this sigma average, by the way, would be equal to this plus r. And in the end, it's either plus or minus r. So again, sigma 1 is actually your sigma average plus the r. Sigma 2 is just sigma average minus the r. So it is very critical to find out the value of the r so that you find the value of the maximum stress based on that. And then you will be able to figure out, which angle gives you which. So that's the concepts over here. You don't have to worry so much about the mathematics. You have to know that we are using the equation in the red color. We try to find the maximum by using the differentiation. And after the differentiation itself, you got the relationships, which is in this box right here. This is the relationships that you got. And from that relationships, you do the substitution, and you find out that in all cases, sigma 1 would be sigma average plus dr. In all cases, sigma 2 would be sigma average minus dr. And we'll find the location associated with that by doing the substitution. And you're doing the substitution of the data that you found, and we'll find out whether or not they're one or the other. Now, data P1 will definitely give you sigma 1. Data P2 will give you sigma 2. And data P1 is actually perpendicular to data P2. That's the relationships that you get. They're 90 degrees apart. Now, what happened here is that we use data P1 or data P2. We do the substitution into tau x prime y prime. And it turned out that this is always going to be 0 because we can, kind of do this. And sine would be tau xy over r plus tau xy. Cosines would be this. So always 0. Always 0. So, at principal stress, there would be no shear stress at all. So that's the main concepts. At data P1 or data P2, tau must be 0. This is something that you must know. Concepts related to the functional forms. One more formula, which is the second one, which is the bottom one. Let's do this. Don't worry if you feel that this is fast. I will slow down when I feel that there's a thing that you really need to know. Okay? So I'll go over the whole thing again, but we just need to make sure that we go through this concept very quickly first. So again, we're going to do the differentiation. Tau x prime y primes, this must be 0, and then of course this would be minus, this would be cosine 2 beta and a 2, tau xy negative, sine 2 beta and a 2. And again, this must be 0. Oh, wait, I already said this must be 0. So it means that from here, I have the relationships, and that is sine of the 2 theta over cosine of the 2 theta must be equal to a negative values of sigma x minus sigma y over 2 over tau xy. The theta that will make this, I will call it theta S1, will give you tau max. Theta S2 will give you the tau minimum. Now, remember the triangle that I have for you before. Let me copy this. This is theta P. In the end, if you want to look at this, it has to go the other way because this one is a negative. 2 of theta s. Actually, 2 of theta s is not like that at all. This is going to be 2 of theta s. Tangent tau xy. I can say that this is negative. So we have like something similar. So which means that we also have the r over here. Perpendicular. Now, what we have from these relationships, this is going to be tangent of the 2 theta, and I will call it theta s. So we use theta s1 or theta s2, and we do the substitution in the sigma x primes. You always going to have the sigma average. Try to prove this yourself. The 2 terms will cancel one another. They always will be 0. Or you want me to just, well, I'll do it. Sigma x minus sigma y over 2 cosines of the 2 theta. Cosine would be minus tau xy over r, and plus tau xy. Sine would be sigma x plus sigma y over 2 over r. So those terms will always cancel. So always going to be 0. So again, sigma x prime will always be sigma average at theta s1 or theta s2, and theta s1 you will get tau x prime y prime, and that's going to be equal to the r. Theta s2 will get tau x prime y prime, and that's going to be a negative r. And that's going to be the basic knowledge of the stress transformation. This is the basic concepts. After the break, we will do exercise. Okay. A lot of work today. Sorry that we have to go through this part very fast. And that's because the whole semester we don't really have that much time. So if you have any question, delay the question until you do the first exercise. Okay, we'll do the first exercise, and hopefully after that first exercise, you will get to understand everything. If not, shoot the question. There's a restroom on the second floor for both female and male. Restroom on the first floor as well. Let's take 15 minutes. Take 15-minute breaks.
เ ที่มันข้อสามเหลี่ยมใช่ปะล่ะเป็นคอร์ดแล้วแรงดันผู้หาแรงผู้เห็นในนั้นมันต้องใช้ค่าของตัวผมรอให้ดูที่เต็มมันเป็นสามเหลี่ยมทั้งในคอร์ดที่มันเห็นผ่านทำไมไม่ผ่านเคียงค้าเราถึงเชื่อเป็นจุดทำไมจะมีทำไมแก้เดี๋ยว